Hi guys, welcome back to another video, and this lesson is going to be another review of a concept that we've seen in the past. And polarity is a concept that we saw when we were drawing out Lewis dot structures. For this unit 9, remember that I won't be testing on the concept of how to draw Lewis dot structures, although it's a good idea to know how to draw some of these structures. But all of the molecules that you'll see today and all of the molecules that you'll encounter in your final Unit 9 assessment, they're already going to be drawn out for you. But you're going to be responsible on how to determine the polarity of these molecules. So, if you want to go back to your notes regarding polarity, you're more than welcome to do so, and I highly encourage it. But this video today will go over in a lot of detail in how to determine polarity of compounds. And we're also going to look at polar bonds, because in order to determine polarity of a molecule, I have to determine whether the molecule has any polar bonds. And polar bonds is a type of covalent bond as well. So let's review first what a covalent bond is. We're going to steer away from ionic compounds and ionic bonds, and we're just going to focus on covalent bonds. Remember that a covalent bond is formed when I have two nonmetals sharing electrons. And so remember that the nonmetals, they're found on the right-hand side of the periodic table. The shared electrons holds these two nonmetals together. And I have an example here at the bottom. So I have chlorine gas. Chlorine gas is Cl2. The element chlorine is found in group 7A to the very right-hand side of the periodic table. Since it's in group 7A, remember this 7 means that it has 7 valence electrons. For Cl2, I have on this left-hand side Cl, I have 7 valence electrons denoted as X's. The other Cl on the right-hand side, its 7 valence electrons are denoted as spheres. Since chlorine is just shy from completing its octet, which means 8 valence electrons, then it's not willing to give up or transfer any of its electrons. So I have 2 of these chlorines, and they're not going to transfer electrons, so the only option they have left is to share these electrons. And the shared electrons that are seen in the middle, this is the glue to this bond. So one shared pair of electrons, that is equal to one covalent bond. So when I share electrons, this chlorine pretends it has a total of 8 valence electrons and it's happy. This left-hand side chlorine is going to pretend it has 8 valence electrons and it's happy. So again, this slide, the main point is that the shared pair of electrons, that is equal to a covalent bond. And sharing of electrons, in this case, it's equal. So there's going to be a lot more examples of covalent bonds where there's going to be an unequal amount of sharing of electrons. And that is due to electronegativity of atoms, and we're going to go over that in just a moment. So let's go over what a polar bond is. And so it's also expressed as a polar covalent bond. Most of the time, you're not going to hear me say polar covalent bond. That's just too lengthy. So I like to keep it short, and I like to just refer polar covalent bonds as just polar bonds, because polar bonds are understood to be covalent. And the polar bond is one where one atom pulls so much more on the electron in the tug of war that the atoms do not share the electrons equally. So I have an unequal sharing of electrons. So electrons from both elements spend more time on the most electronegative atom. So pause this video, make sure that you have these 4 bullet points written down in your notes. On the right hand side, I have images. So let's just focus on the left hand side image where I have a hydrogen bonded to another hydrogen. Remember that hydrogen has only one valence electron, and it would rather have two. Remember that the first shell can only occupy only maximum 2 electrons. Well, in order to satisfy that hydrogen, then it's going to share electrons. So it's going to share electrons with another hydrogen. And so now this hydrogen is going to pretend it has 2, and this hydrogen is going to pretend it has 2. And so they're equally sharing these electrons. But let's look at this example where I have hydrogen and chlorine in a covalent bond. Hydrogen has 1 valence electron and chlorine has 7 valence electrons. Chlorine is going to pretend it has 8 with a shared electron from the hydrogen, and hydrogen is going to pretend it has 2 from one of the shared electrons from chlorine. But chlorine is not going to share these electrons equally. These electrons are going to want to spend more time on the electronegative element, like chlorine. So remember that chlorine is very electronegative, hydrogen isn't. So chlorine is going to hog up all of those electrons, leaving hydrogen bare, no electrons. Sometimes, occasionally, the electrons will go to hydrogen, but it's going to spend most of its time on the chlorine atom, just because chlorine is much more electronegative. So let's just review what electronegativity is. Never mind, learning check, then electronegativity. So just a little learning check. Pause this video and determine which of these bonds is not a polar covalent bond, because it's an ionic bond. So pause this video and take some time to work this out. So I gave you a pretty big hint. Although you don't know how to identify polar covalent bonds, this is questions asking which of these is not a polar bond because it's ionic. So you'll be looking at an ionic compound. So let's look at HCl. HCl is it's made up of 2 atoms, and both atoms are nonmetals. So this has to be a type of covalent bond. OH, also same case, nonmetal. HO, it's the same bond, just flipped. So 2 nonmetals forms a covalent bond. And lastly, I have NaCl. Remember that Na is found on the left-hand side of the periodic table, so it's a metal with a nonmetal, chlorine. So that last option is going to be the correct choice. So NaCl is it's my answer choice because it's an ionic bond, and ionic bonds are never going to be polar covalent. Remember the electronegativity trend from Unit 2? It's a good idea to review the electronegativity trend because it's going to be super helpful in determining whether bonds are polar or not. Remember that electronegativity is an atom's tendency to attract electrons to itself in a chemical bond. And the greater the difference between atom electronegativity values, the more polar the chemical bond formed between them. Francium, that is my least electronegative element, while fluorine is the most electronegative atom on the periodic table. All of the noble gases have no electronegativity value, so just omit them. The trend of increasing electronegativity values increases from francium all the way to fluorine. So elements that are close to fluorine, those are very electronegative elements. And elements that are closer to francium, those are the least electronegative elements. So remember that electronegativity, the trend, the values of electronegativity increases from the bottom left-hand side to the top right-hand side of the periodic table, keeping in mind that the noble gases have no electronegativity values. They're inert, they don't want to react, they don't have any electronegativity values because they already have a full octet. They don't want any electrons. They're happy with what they have. So how do we represent a polar bond? Well, first of all, a polar bond only occurs with covalent bonds. So let's look at the image below. I have an H and I have an F. H is a nonmetal, F is another nonmetal. So this could possibly be a polar bond. My dipole moment, which is an arrow with a tail, and I'll show you what that looks like in just a minute, always points to the most electronegative element. So between H and F, fluorine is the most electronegative element, so I'm going to have an arrow pointing towards F, the one in blue. The dipole moment arrow has a very characteristic slash or dash at the tail. And this is the head that always points towards the most electronegative element. Remember that partial charges, they're denoted with this Greek letter, looks like an incomplete 8. That means that I have a partial negative charge, and the partial negative charge is assigned to the most electronegative element, like this. So I'm going to write down this partial negative sign on the most electronegative element. The least electronegative element gets the positive charge. The bigger the arrow, the larger the electronegativity difference is. So this is how you express a polar bond. So you look whether or not it's a covalent bond first. If it is, then you're going to draw the arrow towards the most electronegative element. And you're going to put the partial negative on the most electronegative element as well, and the partial positive on the least electronegative element. Nonpolar bonds are super easy to remember, and they're covalent as well. And these are bonds that share electrons equally. Two nonmetals with similar electronegativity values, they form a nonpolar covalent bond. And the types of nonpolar bonds are the ones that I have listed here, and it's simply just memorizing these types of bonds. The first type of bond that is definitely nonpolar is bonds of the same element. So for example, chlorine bonded to chlorine. These two atoms, they're the same, so they're nonpolar. The HH bond, also same elements bonded to each other, nonpolar. CC, nonpolar. Any combination of atoms that are bonded with each other, those are nonpolar bonds. And that's because you have an equal amount of sharing. The electronegativity values of both atoms of equal atoms, it's the same. You need to have a drastic electronegativity difference of atoms for there to be unequal amount of sharing. And the bond that you're going to have to just memorize that is nonpolar is the CH bond. So the CH bond is always a nonpolar bond. And the reason behind that, it's because carbon and hydrogen have similar electronegativity values. So because the electronegativity value is equal or close to being equal, then both are not going to pull harder than the other on electrons. They're going to share these electrons equally. With that being said, nonpolar bonds, they're really easy to identify. Anything else will just be a polar covalent bond. So let's do a little quick learning check. Number 2, that talks about, or that tests you on what a polar bond is. So which of these 4 bonds is a polar covalent bond? And the biggest hint that I have for this, look for the non-polar bonds first. So pause this video, determine which of these is non-polar and which is polar. Well, the first one is CH. Remember that that's the bond that you have to memorize as non-polar, so it can't be the first bond. O bonded to O. element bonded to the same element is a nonpolar bond. Therefore, it can't be OO or CC. HO is not any of those bonds that I talked about in the previous slide. So HO is a polar bond. So the last choice will be your answer. Learning check number 3. Which two bonds are nonpolar covalent bonds? So pause this video, take a moment, look at all of the bonds and determine which one's nonpolar, and then after you decide which one's nonpolar, all the rest are going to be polar. Alright, let's start with CLH. Well, Cl is very electronegative, H isn't, so there's a huge electronegativity difference between both elements. So CLH is very polar. HI is on the 7A column, and anything on the very right hand side is generally very electronegative. So HI is a polar bond. CO, polar. CH, that's the one that you memorized, that it's not polar, so it's going to be that one. And CC, it's an element bonded with the same element, so non-polar as well. So it's those last two. Make sure that you understand how you can identify non-polar bonds from polar bonds. So let's talk about non-polar molecules, and these are easier to talk about than polar molecules. So non-polar molecules are, that's when I have a molecule whose electron density is distributed symmetrically within the molecule. That means that electrons are shared equally with the entire molecule. And a molecule will be nonpolar if it contains only nonpolar covalent bonds. So if my molecule is composed of just nonpolar bonds, then that means that my whole molecule will just be nonpolar. I cannot have a nonpolar molecule. I cannot have a polar molecule without any polar bonds. So this first one is super important. A molecule will be nonpolar if it only contains nonpolar bonds. But nonpolar molecules can have covalent bonds. So if two or more polar covalent bonds are arranged symmetrically within the molecule, then I have a nonpolar molecule as well. So I have these two images. The first image talks about the first requirement. It contains only nonpolar covalent bonds. This CH4 molecule, which is methane, it's only composed of CH bonds. So remember that CH bonds are nonpolar, and this has to be a nonpolar molecule because that's the only type of bonds that I see. Let's look at this molecule, CO2. This is carbon dioxide. CO is a polar covalent bond. So my dipole moment arrow points towards the most electronegative element. So I have two of these bonds and I have two of these arrows. But notice that this molecule is very symmetrical. So if I cut this in half from top to bottom, or I cut this in half from left to right, have the identical mirror image from left and right, or top and bottom. These arrows, they're pointing directly opposite from one another. So these moment arrows, you're just going to end up canceling. And if I don't have any dipole moment and I have a very symmetrical molecule, then I have a nonpolar molecule. Polar molecules. And that's when I have a molecule whose electron density is distributed asymmetrically throughout the molecule. And the molecule is going to contain a partial negative and a partial positive charge. A polar molecule must contain at least one polar covalent bond. So without any polar covalent bonds, then I have a nonpolar molecule. And for a polar molecule, I need at least one polar bond. But I have different scenarios for a polar bond, or a polar molecule, sorry. A molecule is polar if it contains exactly one polar covalent bond. We're going to see examples of all of these three requirements. Two or more polar covalent bonds are arranged asymmetrically within the molecule, and dipole moment arrows do not cancel out, and I'm going to have a net dipole moment. And the third scenario, a molecule has at least one lone pair in its central atom. So if I have any of these three requirements that is met, then I'm going to have a polar molecule. So let's look at the first requirement. Let's suppose I have a molecule with just one polar covalent bond. So let's look at HF and CLH and HI. These three bonds, they're actually molecules as well. This is hydrofluoric acid, a molecule of hydrofluoric acid. This is one molecule of hydrochloric acid, and this is one molecule of hydroiodic acid. Remember that the dipole moment arrow always points towards the most electronegative element. That would be fluorine, in this case, chlorine, and iodine. And the most electronegative element on the molecule or bond will get the partial negative. So fluorine will get the negative, chlorine will also get the negative, and iodine will get the negative. And that's because they're the most electronegative element of the two. Let's take a look at the second scenario. So two or more polar covalent bonds are arranged asymmetrically within the molecule. So in order for a polar molecule to be polar, I need to have at least one polar bond. Let's look at the first image. So I have a CH bond. Remember, that is a non-polar bond. So this bond is non-polar, but the other three bonds, the CF bond, those are polar. Notice that the general direction of these dipole moments, they point towards the bottom. So the general net dipole moment, which I'm going to denote it as a yellow arrow, points towards the bottom. So this yellow large arrow that points towards the bottom, that is known as my net dipole moment. And the dipole moment arrows, they're arranged asymmetrically. Let's look at the second image. This second molecule, it has two CH bonds, so I know that these bonds are nonpolar and they're not going to have an arrow. But I also have two CCl bonds, and I know these for sure are polar. So I'm going to draw a dipole moment, and remember that the arrow points towards the most electronegative element. My general direction of these two arrows is somewhere in between them. So my net dipole moment is going to be in between these two arrows. Because I have a general direction, then that means that these molecules are going to be polar. And they're asymmetrical because the dipole moment arrows are not distributed symmetrically. It's very asymmetrical looking. And the third example, a molecule has at least one lone pair in its central atom. So this molecule has a central atom, which is in this case oxygen, and I have two lone pairs. That automatically tells me that this is a polar molecule. NH3, which is ammonia, I have one lone pair. Again, that is I just need at least one lone pair for this molecule to be polar. And so both of these molecules, because they have a lone pair in its central atom, they're polar molecules. And they also have a net dipole moment, that is the general direction of these two arrows, and the general direction of these three arrows is also pointing towards the top. So these are the steps in order for you to determine if a molecule is polar or not. The first step is to draw your Lewis structure. For this unit, I will always give you the Lewis structure. So it's not a concept that I'm testing you for this unit. If I have 0 polar covalent bonds, then my molecule is automatically non-polar. If I have just 1 polar covalent bond, then I have a polar molecule. But things start to get tricky when I have 2 or more polar covalent bonds. So what you're going to do when you have identified that you have 2 or more polar bonds, you're going to draw the direction of the dipole moment for each polar bond. If the dipole arrows are arranged symmetrically, then it's a nonpolar molecule. If the dipole arrows are arranged asymmetrically, then I have a polar molecule. And before I finish off, let's do a little quick learning check with all of the things, all the information that I just mentioned. So I have 4 molecules. You're going to determine which 2 molecules are non-polar. So remember what a non-polar molecule consists of. Pause this video, give it your very best shot. We're going to look at these molecules one by one, and let's focus on the left-hand side molecule. So I have CF3H. This molecule, CH bond, I know for sure that is non-polar, but the CF bond right here is most definitely polar, and I have 3 of them. So I have to determine the dipole moment arrow of these bonds, and remember that the arrow always points towards the most electronegative element, in this case fluorine. So I have 3 arrows pointing towards the fluorines, and because these arrows are arranged asymmetrically, this molecule itself has to be polar. Let's look at this molecule, Cl2, H2. Again, these 2 bonds, CH bonds, they're non-polar, but I also have a CCl bond, which is polar. My dipole moment arrows, they point towards the most electronegative element, so I'm going to have 2 arrows pointing towards the chlorine atoms. So my arrows, they're arranged asymmetrically. I have one that's pointing straight up, and I have one that is pointing towards the left bottom side. So the arrows, they're not going to cancel out, and I'm going to have a general net direction in between these 2 arrows. So because the arrows are not distributed symmetrically, this has to be a polar bond or molecule. Sorry, so this has to be a polar molecule. Let's look at this third molecule, CO2. I have to identify whether or not I have polar bonds, and I do. I have a CO bond. This CO bond is a polar bond, and so its dipole moment arrow points towards oxygen. But I have 2 of these bonds. I have another arrow pointing towards this oxygen. So because the 2 arrows are pointing completely opposite of one another, those arrows are going to end up canceling. And these dipole arrows, they're arranged symmetrically. So because this is a symmetrical compound, even though it has polar bonds, it's a non-polar molecule. And that's because of the symmetry. Alright, let's just focus on the last molecule. So I have C3H8. So this molecule is known as, propane, I think. Or it's butane. I don't remember. I don't even know. Alright, so this molecule, I have a bunch of bonds. So I have this CC bond. Remember that a bond is nonpolar if it's bonded to the same element. So this bond, nonpolar. This bond is also nonpolar. Let's look at other bonds, CH bonds. I have a lot of those. I have 8 CH bonds, and all of them are nonpolar. So this whole molecule itself has no polar bonds. Therefore, this molecule has to be nonpolar. So the answer are these two molecules, the CO2 bond and the C3H8 molecule. And this is the last slide, and these are key characteristics of polar and nonpolar molecules. And the biggest reason why we talk about polarity is because we want to know what's able to dissolve in water or not. Remember the concept like dissolves like. Polar substances dissolve other polar substances. Nonpolar substances dissolve other nonpolar substances. And when you mix polar and nonpolar substances, they do not mix. Because water is a polar substance, polar substances are able to dissolve in water, but nonpolar substances are insoluble in water. So, for example, nonpolar substances are generally like vegetable oil. Vegetable oil is a nonpolar substance, and I know that because it doesn't mix with water, and I know that water is a polar molecule. Let's talk about the relative melting and boiling point of polar and nonpolar substances. Relatively, the melting and boiling point is usually higher for polar substances, and the boiling and melting point for nonpolar substances is relatively lower. So these are the two types of characteristics that I want you to get from polar and nonpolar substances. The first one being the most important characteristic of a polar and nonpolar substances. So that is it, guys. Thank you so much for tuning in. Make sure that you log in to Teams and get the assignment done. That assignment is due Wednesday. So have a great day, guys. Take care. Bye-bye.